Recording in progress.
Okay, today we're going to talk about sequences. And this is the first building block in our road to construct Taylor series, which we will get to in a little bit, not today. But Taylor series are very interesting and kind of the point of Calculus 2, because they let you represent any function as somewhat polynomials. We'll get there. So really what a sequence is it's just a list of numbers, and the list can be infinite. In fact, that's the case that it is. So an infinite list of numbers. And we're going to represent a sequence by A1, A2, A3. It's all these numbers. And this list keeps going on forever. We can visualize a sequence just by plotting these numbers over the integers. So instead of plotting over the real line, we'll plot over the integers. But you can actually, if you just plot these points like so, you can actually plot this over the real line if you like by using a bar graph. So this is, and then this list, it just keeps on going. And so you can think of a sequence as just like an integer, a function on the integers. So it's kind of like f of n, or really a of n, versus f of x. And so looking ahead, so if a of n is like f of x, then the integral of f of x, there will be some sort of integral. Really, it's going to be an infinite sum of the an's that we'll be considering. So again, we'll get there. But that's kind of where we're headed. So let's just start off with some examples of sequences. An equals n, for example, that represents this list. So a1 equals 1, a2 equals 2, and really it's just this list, right? 1, 2, 3, 4, 5, and so on. It's this infinite list of numbers, which you could plot like so. And if I did instead an equals 2 times 1/2 to the nth power, and I'm starting, and my list is index number 1, 2, 3, 4, then if I actually plug in n equals 1, you see that the list actually starts with 1, not a half. So we have 1, 1/2, 1/4, 1/8, and really what's happening is we're decreasing by half at each step. Another example that will show up very frequently is 1 over n factorial. So here's what a factorial means. 0 factorial is defined as 1. The triple lines, this means def, or definition. So 1 factorial is also defined as 1. So now here's where things get a little more interesting. 2 factorial is going to be 1 times 2. So it's equal to 1 factorial times 2. There's going to be a pattern here, recursively defined. So 3 factorial is going to be 2 factorial times 3. So in other words, it's 1 times 2 times 3, or 6. And then 4 factorial, you can see where this is going, right? This is going to be 3 factorial times 4. So it's 1 times 2 times 3 times 4. 4 is the extra number that shows up in the factorial. So it's going to be 24 in this case. So 5 factorial, you can see, is just going to be 4 factorial times 5. 6 factorial is going to be 5 factorial times 6. So it's going to be 1 times 2 times 3 times 4 times 5 times 6. And I'm not going to write what this actually is any further. So it turns out this is going to be 120. This is going to be 720. These grow very big. So factorials are big if n is large. In fact, n factorial, it grows faster than n squared. It grows faster than e to the n, and pretty much any other function you can think of. So factorials, you can think of as dominating everything else. N squared, e to the n, n factorial is bigger than anything else. They roughly that you can think of, that's straightforward. So yeah, so the factorials will show up very often for reasons I won't get into. The last thing I will do in this video is I just want to go do the reverse. So if I start with a list, let's see if we can deduce the an, the closed, this is the closed form expression. So here's the list. The list is 2/3, 4/5, 6/7, 8/9, and it repeats as such. It doesn't actually tell you what the rest of these are. You have to guess the pattern. So you can see it's like this is the wrong way. 0.67, 0.8, what is this? 0.86. And what is this? This is like something like 0.88 or something like this. You should not look at the decimals. This is the bad way. So instead, we're going to list the numerators and the denominators versus n. So here's what I mean. I'm going to put n here, I'm going to put the numerator here, and I'm going to put the denominator here. So let's start with n equals 1. We have 2 and we have 3. I don't see anything so far. Now, and for n equals 2, I have 4 and I have 5. For n equals 3, I have 6, 7. For n equals 4, I have 8 and 9. Now it's a little better. So here, I can see that this is actually, this 4 looks kind of like 2n. And the 6 looks like 2n. And this 8 also looks like 2n. So clearly the pattern is, in general, if I have n here, I should get 2n. So I think that's pretty good. So now we just have to figure out what's going on with the denominators. So 3 is 2 plus 1. 5 is 4 plus 1. 7 is 6 plus 1. 9 is 8 plus 1. So we know this is 2n plus 1 in all cases involved. So in other words, the numerator divided by denominator is going to be 2n divided by 2n plus 1. So therefore our an is going to be 2n over 2n plus 1, and our n's are going to be range from 1 to 2 to 3 and so on. In other words, not starting at 0 in this case. Okay, thanks for watching.